Okay, today is day 4 of Math 141. We actually had a little meeting out in the hallway yesterday, but that was not on videotape. So this is our 4th day in the classroom. According to the syllabus, we're still in a pre-calculus mode. And what we should be doing this week in this course is section 1.3. We've done that, new functions from old functions. Section 1.4, we will get to that, but that is graphing calculators and computers. How many of you have a graphing calculator in here? Does everybody have a graphing? You don't have to have one. Make sure you bring that with you the next couple times, and we'll talk about some graphing calculator type issues. Certainly we'll talk about the computer issues when we get to Maple. Today I'd like for us to work in the back of the book in the appendix. In making up this outline, we thought it was appropriate for us to review kind of anything and everything related to lines, and similarly with circles, and that's in the back of the book. And then also conic sections. When I say conic sections, does that ring a bell? I hope. So what do you think of when I say conic sections? Not the comic section, that's on the Sunday paper. This is a conic section. Hyperbola, parabola. A circle is a conic section. We'll look at that today. It's kind of off by itself because it's one of the simpler ones by definition, and also the functions that result. So we'll look at the conic sections, their definitions. You may or may not have done that in a high school class, but we think that's important going into a calculus course. So we're where we should be, and we're still in that pre-calculus mode. And the task today is with Appendix B. In the back of the book, I'm looking at page A7 in the back of the book on coordinate geometry. And we will look today, and hopefully this is review, look at circles and lines. And that clearly is related to calculus. We'll look at functions, linear functions. And I'll try to explain today why we'll need that. And we'll look at circles in a variety of ways in this course. And 241 also. And I guess the three-dimensional counterpart of these, a sphere, in Calc 3. So let's do that. Appendix B, you'll see the first thing that's listed here is the distance formula. Let's actually back up just a tad from that, so just to make sure we're all on the same page here. We're going to be talking about the Cartesian coordinate plane, the two-dimensional plane. Typically we call that the x-axis and the y-axis, but it might be a variety of things. They don't have to meet at right angles, but we normally have them meeting at right angles. It's just a lot easier that way. Things work more normally the way we like them to work when we have our axes meeting at right angles. And we've subdivided our Cartesian coordinate plane into 4 regions called, what do we call those? Quadrants. Okay? And we can characterize the points in those quadrants based on basically the signs, right, of the abscissa and the ordinate, abscissa being the first element of the ordered pair and ordinate being the second element of the ordered pair. So if they're both positive, we're in the first quadrant, both negative, we know where those are, right, based on the location of points. So let's take issue with this distance formula. We've used it a lot. Let's backtrack into the Cartesian coordinate plane, see if kind of where it's grounded. I think this is helpful. So let me kind of arbitrarily establish a couple of points, x1, y1, and x2, y2. And our task is to find the distance between them, and you all know that. You've used the distance formula many, many times, but where does it come from? So this is what we're looking for. Let me call that D. So that's what we're looking for. Since we are working in the Cartesian coordinate plane and the axes are meeting at right angles, let's find this point, which is the intersection of the horizontal line through here and the vertical line through here. So we can establish a right triangle. That point is x1, y1. What are the coordinates of that new point? Do we have enough information to find those two coordinates? I don't want to call it x3, y3. We don't have to do that.
X2, Y1.
Okay, x2 y1. How do you know that?
It's equal with the X.
Go ahead.
It's even with the X on the X coordinate.
Okay.
The X,
It's got just as much x as this point, right?
It has, yeah, just as much Y coming up from the
Okay.
first point.
Everybody follow that all right?
Mm-hmm.
It's over from the y-axis just as much as this point, which has x-coordinate x2, so it also has x-coordinate x2. It's up from the x-axis just as much as this point, so if this is up y1, this is also up y1. Okay? And now we can use the Pythagorean theorem, since we have a right triangle. Leg squared plus leg squared equals hypotenuse squared. So what's the length of this leg? 2 points in the same horizontal line. How do you find the distance between them? You don't need the distance formula for that. This one's over here, x2. Right, there we go. x2, and in fact, if x2 is a larger number, x2 minus x1. And just in case that it doesn't really look like what my diagram looks like, let's make sure it's positive. We'll take the absolute value of their difference. And this leg, this point's up here y2, and this point's down here y1, so we want the absolute difference of those two. What is it? Okay, absolute value y2 minus y1. So if we're looking for d, the distance between our two original points, d squared is this distance squared plus this distance, the other leg, squared. Everybody go along with that? Okay. Just leg squared plus leg squared equals hypotenuse squared. Does it really matter at this point that we have absolute value? Doesn't matter because we're squaring the results. So that's d squared. We don't want d squared. We want d. So we need to do what?
Take the square root.
Take the square root. And there's our old friend, the distance formula. Okay? So I don't know that we need to spend our time today, but I've asked you to look at some problems at the end of this section that just kind of refresh you on the use of the distance formula, that you know how to plug in your two x's. It doesn't matter the order because you're going to square the result. Plug in your two y values. Again, order is irrelevant. Square the result. Add those two things together, take the square root. And we want the principal square root, right? Because it is a distance, which is a positive number. All right, now why would they review us on the distance formula before we get into circles? Well, let's see if we can derive that equation of a circle. Circle by definition, in fact, you know the definition of a circle. Somebody tell me what would be a good definition for a set of points that would be a circle in the plane. And this will be a good time for me to learn names too. JJ.
It's all the points are equidistant from a center point.
Okay. Can anybody add anything? I like that. Anybody want to kind of qualify that or clarify that just a tad? He said the set of points equidistant from a given point. Am I paraphrasing that okay? Anybody want to qualify? I want somebody to qualify that or clarify that just a little bit.
There are an infinite number of points on the circle.
How about in a plane?
Okay.
In a plane, because what JJ said and then what I paraphrased, if that were not in a plane, couldn't that be a sphere? Right? So we want the set of points in a plane equidistant from a given point. Does that work for everybody? Okay. So let's take that definition. If I can get a pen that's actually going to work here. And I'll try to match what we see on the screen here. For the center point, we'll just call arbitrarily the center point some point h comma k. And then we'll take a point out here, r units. And let's call that any point on the circle, x comma y. If you see a point that doesn't have a subscripted like x1 or x2, then that's probably going to represent all the points of that set. So that could be any point on the circle. When you see an x1 or x2 or y1 or y2, that's a specific point. So we want all these points on this thing, this circle, set of points, equidistant from this given point. So we need to use the distance formula, equidistant. So somebody tell me how I can take what it is that I've laid out here and establish an equation that we can kind of massage a little bit and get the equation of a circle. Distance from what to what is what?
Distance from x to h is from that point to the other point as a radius of the circle.
Okay, everybody all right with that? So the distance from any point on the circle, which I've called x, y, kind of any point on the circle, to the center point, hk, is r. So the distance from xy to hk is r. Does that work? Right? There's our friend that we just reviewed, distance formula. Difference of the x's squared plus the difference of the y's squared is the radius. And that's not exactly what you see over there. So what do we have to do to get that? Square both sides. Okay? So if we square this square root, we get what's under the radical, and if we square the right side, which is the radius, we get the radius squared. So there's our kind of general equation for a circle. We'll do a little bit more with this than we did with the distance formula. And then you'll see this guy here at the bottom is a simplified version. If you see just x squared plus y squared equals r squared, then that is a simpler version because hk is really what? 0, 0. So that has center at the origin. And you say, well, this is not a function. Circles are certainly not functions. I'll agree with that. Even though we simplify it, that's not a function either. But we want to be able to take something that's in this form and possibly solve it for y and take one of the two pieces. So let me do that. Do that next. Let me move over to here. Let's take an equation of that form. Okay, so we know what about that? That's a circle. Center at the origin, radius of 4. Okay, and we know that's not a function. Let's go about solving for y. That would be our first step in trying to solve for y. And taking the square root of both sides. Now I did take the square root myself, so I have to allow for both possibilities, plus or minus. So I end up with the principal square root and the negative of that. Isn't each piece there a function? Tell me what this is. This is kind of, I'm trying to get to why it is we would review some of this stuff.
Is it a semicircle?
That's a semicircle. Which one is that?
Top half
That's
positive
the
part?
top half, right? Isn't this the upper semicircle? This is the lower semicircle, right? So we can talk about circles. Now, maybe not, we don't want to talk about the whole circle, but we can talk about the upper half as a function. It is a function. And the lower half as a function. And if we talk about the whole thing, we want both parts together. That's even easier. We can use this guy right here to talk about that. Okay, any questions about that? I'm going to take that one off the screen. Anything about that? Okay, let's take a look at this. Tell me what you think this is. What about that? Well, we're talking about circles. It's probably a circle, right? But that's a disguised circle that's very much different from the kind of the standard form that we're used to seeing that we developed over here. Can we take that form, and have you ever done anything like this before, where you take this version of a circle and put it into that form, that standard form? A couple of you shook your head that you've done that. So how should we go about taking this kind of expanded form of a circle? How do you recognize this as a circle?
X squared, y squared.
Okay, the sum of the squareds. Okay. Now, the sum of two squared terms could be an ellipse. So how do we know this is a special kind of ellipse? This is a circle as opposed to any other type of ellipse. Okay, the coefficients are the same. Okay, we have one x squared and one y squared. So that when you see the sum of the squared terms, that's an ellipse. And when the coefficients of those squared terms are the same, that's a special ellipse, which is a circle. And we'll review ellipses before we get out of this appendix. But this is a circle. So tell me what to do now to put it in a standard form.
Isolate the x and the y and complete the square.
Okay, I like both those. Let's get the x's together. Leave some space because she said we're going to complete the square. Get the y's together. Leave some space to allow completion of the square. And get anything else on the other side. So we'll just cast that 13 over to the other side. It becomes a negative 13. Got to subtract 13 from both sides. So we want to get a perfect square in x and a perfect square in y. What completes the square in x? Okay, keep going with that thought. You're not quite finished yet.
Gotta square it.
Okay, negative 2 squared. There we go. You guys can work together now on all your tests and quizzes. You'll get them right. So we take half of this coefficient. Does that ring a bell? Half of this coefficient squared would be plus 4. Now what did I just do to the left side? I just added 4. I can't do that without also doing what? Okay, I could add 4 to the other side. That makes that legal. Okay, what completes the square in y? Plus 25. Take half of that coefficient squared. What did I just do to the left side? Added 25, so we've got to do that over here. Everybody okay with everything that just happened? Okay, this thing now, hopefully, is a perfect square. this thing is hopefully a perfect square. And on the right side, we just got to deal with whatever's there. So what do we have? 29 minus 13, 16? Now, don't expect it to always work out to a perfect square, but it did in this case, which is nice, because that side is the square of the radius. What binomial squared is that? X minus 2, thank you. Y plus 5, thank you. And now we're in a standard form. This looks more like a circle. The center,
2 negative 5.
okay, remember now to keep track of signs. I like that answer. H is what is subtracted from x, right? And K is what is subtracted from y. Why is it subtraction? Let's track that back just a little bit. Why does H have to be subtracted from x? Well, because how did we do that? Didn't we use the distance formula? Right? And what operation is used in the distance formula? Subtraction, right? So it's x minus h squared. So what is subtracted from x is 2. What is subtracted from y? Negative 5. And if it's addition, that's subtraction of a negative. And the radius is 4. So if it's in an expanded form, we can complete the square in the x's and the y's. Make sure you add whatever it is you added to both sides and get the standard version of the circle in that fashion. Suppose we come up with something like that. We do all this work, and we come up with something for our bottom line that looks like that. I'm not liking that. So what about if we backtracked all the way back to our original equation? What would you say about that set of points? There really isn't a set of points, right? So when we try to put it in a standard form, if this is what we get, you say that's a set of points, circular in the plane with radius, or excuse me, center at 3/8 radius, square root of negative 3? I don't think so. So there is no such set of points, right? No set of points that satisfies that particular equation. All right, let me finish with suppose we work it all out and we end up with that.
It's just a dot.
That's just a point. That's exactly right. Now, is that a circle? Yeah, technically it is. I mean, our definition was what? The set of points in a plane equidistant from a given point. Well, how far away are they? 0 units, right? So it's not a very big circle. So that's pretty appropriately called a point circle. So technically you can call it a circle because it does fit the definition. That's, I guess, since we're speaking technically here, that would be called a degenerate circle. It's a degenerate conic. Is that that's kind of the smallest it can get, right? And it really, I guess if you want to go other than technically, it's really not a circle, it's a point, but it does fit the definition. So we would have to call that a point circle. Okay, enough for circles and the distance formula. Let's go on to lines. Let's talk briefly about this before I take this sheet away. In this appendix in the back of the book, they want us to review kind of anything and everything about lines. So we want to first review slope, then use that to develop forms of linear equations. The point slope form, if you're given a point, you're given the slope, can you develop the linear equation? the slope intercept, if you're given the slope and the y-intercept. This is old hat, isn't it, in this old stuff? And then dealing with parallel and perpendicular lines. So I don't think we're going to stretch you too far today, but hopefully we're reviewing some things. I'll put this back up. One of your questions might be why? Why, we're going into calculus. This is pre-calculus stuff. How are we going to use slope in a calculus setting? Well, let's say we have a curve that looks like this in a plane. One of the tasks that we may be asked to do early in a calculus problem is at a certain point on a curve, find the equation of the tangent line. So we're going to have a way, the derivative, to find the slope of the tangent line to the curve. We're not ready for that quite yet, but it's right around the corner. And once we are able to find the slope of that tangent, we will take that point of tangency and that slope, which we'll find using the concept called the derivative, and we'll be able to develop the equation of that line with some prior knowledge, what we're reviewing today, and some new stuff when we get into the calculus. So finding linear equations will be a part of a calculus course, even though a lot of the background is in a pre-calculus course. Okay, the idea of slope, let's go with that. I'd certainly like to know why we have a fetish there with the letter M for slope. I don't know that. Sometimes I know why they picked the letter they use. I don't know why they picked M with slope. If you have some insight into that, let me know. Kind of the old elementary definition is the best, I think. The old rise over run, I think that's a pretty good description of what slope is. And then you can apply that to whatever coordinate plane situation you have. Typically for us, that's going to be the difference of the y's over difference of the x's. Could the slope of a line be 0? Tell me about that line. Horizontal line, right? Now think about that for a second. If the slope is 0, what makes a fraction 0? When the top is 0. When the numerator is 0, the denominator can be anything you want it to be except 0. So that could be, let's say, 0 over 5. Now if we go back to the rise over run definition, is that true about horizontal lines, that they have 0 rise and as much run as you want to give them? I think that's all they do, isn't it, is run? They don't rise at all. So those are horizontal lines. Can the slope of a line be undefined? What would make a fraction undefined? 0 in the denominator. Well, can you think of lines that have all kinds of rise and don't run at all? Vertical lines, right? So that seems to also fit our kind of elementary. Now there is some textbooks, and I know this for a fact because I've taught out of them, unfortunately, that use the term, I'm not even going to write it down, I'll mention it, no slope. Okay? Have you ever seen that in a math textbook or ever had a math teacher? Okay, some of you are shaking your head, yes. That's an awful term, no slope. I know when I reach in my pocket and I have no money, I know what that means. Don't you know what that means? My wife is in the back of the room. I reach in my pocket and have no money. Very familiar feeling in our household. That I have 0 money, right? Doesn't no money mean 0 money? I don't know what no slope means, to be honest with you. So let's not use it, okay? It's either slope 0 for horizontal lines or slope undefined for vertical lines. So we're going to completely throw out the terminology that I used previously, that I will not use again. Okay? Slope 0 or slope undefined. If the slope is positive, tell me something about those lines as you view them in the plane. Describe them to me.
It's rising as it goes right.
Okay? As it moves to the right, it would be on its way up, right? So increasing, would that be a... As you read a graph like you read a page of a book from left to right. So as you read it from left to right, it's increasing. Now curves, this is all related to lines, and I know you're saying, yeah, I know this, let's get on to something really good. The reason why we're hitting this stuff at the beginning of this course is lines can be increasing, and you know that, but curves can be increasing too. What would you expect to be true about a curve where it is increasing? Wouldn't you expect the slopes of the tangent lines to be positive? Does that make sense? So we've got this curve that's increasing. Okay? Let's take a tangent line right here, or a tangent line right here, or a tangent line right here. What's true about all the slopes of all those tangent lines to the curves? They're all positive, right? So it's a valid thing to review the fact that if a slope is positive, that means in that general vicinity the curve is increasing. And if the slope is negative with a line, that line is what from left to right? Decreasing or falling. Same thing with a curve. We will analyze a curve at a variety of different points. And if the tangent line at that point is negatively sloped, that curve at that point is on its way down. So those are simple things, but we're going to use them in a different context in calculus. Okay, let's take our definition of slope. I'm going to alter it just slightly. Let's say one of the points we know, and the other point we want to represent all points on that line. Is this thing is called the Elmo. Is this working better than the board for you? Is this okay? I like to be up and moving around, but I'll sit if it works better for you. Use this more? Yes? Okay. So this is, the 2 points here are some general point, xy, and some specific point, x1, y1. So I want xy to represent all the points on the line, and then x1, y1 to be a specific point on the line. Y minus y1, x minus x1, there's our slope. Everybody all right with that? M is the same as m over 1. Now I want to cross multiply. Does that look familiar? Typically we call that the point slope. Form of a linear equation. Pretty appropriately named, because if we know a point and we know the slope, we just plug them in and we got the equation. So once again, we're going to be finding equations of lines that are tangent to curves at certain points. So this will be our old friend here will be called into service. So if we know that a line goes through the point 2, -5, and has slope -1/4, could you find the equation of that line? Okay? Could you find the equation of that line in that form? With a, b, and c, what I would call relatively prime integers, meaning that there's no like factor in a, b, and c, so they're all integers, but you can't divide by something in all 3 cases. All right, well, let's see what we would do. Y minus the y value equals slope x minus the x value. Everybody's confident with that, I hope. I want to get rid of the fraction, so I need to do what?
Multiply with x minus.
Multiply both sides by 4. Will that work?
Yeah.
So this 4 and this 4 will knock one another out. So we've got 4y plus 20. Does that look all right with everybody? That computation? And now let's put everything on one side. So how about x plus 4y, what? Plus 18? Do you remember how to look at an equation in this form and pick off the slope? Ax plus by plus c equals 0 form, and determine from that form what the slope of that line is? What is that? How do we do that?
Over 2a.
Negative b over 2a, is that right? That's something, right, in your past? Don't you remember that? All right, well, let's see. Let's say we started with that, and we're kind of headed, I mean, this is a directed question to what we're reviewing next. That okay? I want to solve it for y. If I solve it for y, I have another form. What's that called? Y equals something x plus something. Slope-intercept form. So I know if I can solve it for y, I can find the slope. Divide everything by b. Now let me ask that question again. When it's in kind of a standard form, ax plus by plus c equals 0 form, and we wanted to pick off the slope, what is it? There's the slope. And isn't this the y-intercept? Right? So the slope is the negative of a divided by b, where a is the coefficient of x, b is the coefficient of y. And the y-intercept is the negative of c, where c is the constant, divided by b. Now back up to our example. What's the slope from our final version there? Negative of a over b would be negative 1 over 4. Wasn't that it? Wasn't that our slope when we started? And then what new knowledge do we have, or can we pick off from that? We can pick off the y-intercept, which is negative c over b. Okay, so there's our other old friend that we need to take a look at today. Our slope-intercept form. So if you can solve it for positive 1y, then the coefficient of x is the slope, and the other number tacked on there at the end is the y-intercept. If you don't believe that, use the point slope form and pick the point specifically to be the y-intercept, which is what, 0b, and you'll come up with this. Let's suppose that, and these are easy, but let's suppose that the slope is 2/3 and the y-intercept is 5. That's kind of a plug and chug kind of thing. right? And if we needed another form, we could clear fractions and multiply. Whatever other form we need, we can go from there. Last thing. Let me make sure it's the last thing. Let me throw this in. The authors throw this in the back of the book. Let me just make one up. Suppose we have an inequality. So we need to know about equations so that we can deal with things that are not equations and figure out where those points are as well. Any suggestions, recommendations to deal with an inequality that obviously is linear, right? Got a linear inequality?
Don't you can solve for y, get it in mx plus b form, then the shade.
Okay. And how would you recommend shading? Not like, X's or lines or whatnot.
Just it's going to be below the line.
Okay.
I had to look at it first.
Okay, well, let's take your first suggestion. Let's solve for y. Now, as long as we do the same thing to both sides, we're still in business, right? Even though it's an inequality. We can divide everything by 2. Now, keep in mind it's an inequality. If we were dividing by a negative, what would we have to do? Rearrange the order of the inequality. So we didn't, so it maintains the same order. Now, would it be helpful for us to know how to graph? I don't know where that came from. Would it be helpful for us to know how to graph the line y equals negative 3x plus 11 halves? Okay? Do we want that to be part of our final set? It is, because it's less than or equal to, so certainly y equal to that is part of our final answer. So let's graph that line. So 11 halves, 5 1/2. That's our y-intercept. And how do I give something a slope of negative 3 halves?
Oh, up 3 left.
Or down 3 left.
Okay, so some combination of down right or up left. Will that work, right? One positive, one negative movement. Let's go down 3. So there's 1, 2, 3, and right 2. That work? And you might want to check. I do want this line to be part of the solution set, so I do want a solid line. If it's not part of the solution set, I would just make it a dotted line. Now, we've got 2 possible sets of points. Actually, there's 3 possible sets of points. One of them we already have. That's the line itself. That's part of our solution set. The other 2 are the sets of points above this and the set of points below this. Now, if you're not sure which you want, try one, right? Try points above, points up here. Just pick a point and try a point below and see which ones work. Or you could go by this. Y's, the y's are less than or equal to. Where are y's less than or equal to? As you work down the y-axis or as you work up the y-axis? As you work down. So pretty sure we're going to shade the region underneath this, but let's pick a point and try it. Let's pick a point above and show that it's not in the solution set. Give me a point that's above this line. 0, 6, right? So is that in the solution set? Well, if it's in the solution set, here's our original. No, it's not. There's our original inequality. So if I take 3 times the x value plus 2 times the y value, are we less than or equal to 11? No, we don't want them. We don't want any of them. Because that one point fails, every point in that region fails. So we could try a point underneath. They're going to work. All of them are going to work. So we want this line to be a part of our solution set, and we want all points under this line to be a part of our solution set. So there's another situation where a linear equation comes in handy, even though we have an inequality to deal with. Okay, last thing, and that is parallel and perpendicular. I don't think this is rocket science, so let's just mention it and go on, that if lines are parallel, their inclination in the plane is the same. They should have the same rise and run quotient. So the two lines should be, their slopes should be equal. So those lines are parallel. What happens with the two lines in the plane if they are perpendicular? Negative reciprocals, right? So you could say this way, and actually this is kind of a testy little thing to prove. You ever notice this in books? Up to and including, well, up to pre-calculus anyway, they never have a proof for this. Someday we'll dive into why this is true and actually prove why the product of the slopes is -1, or you may be used to this version, that they are negative reciprocals of each other. That's not a real simple validation to prove that that is in fact the case. But we've seen and used that for several years, that the product of their slopes is -1, or they are negative reciprocals of one another. If you see equations in this form, clearly those are two parallel lines, right?
Mm-hmm.
What's the slope of each one of them?
3 by 2.
-2.
Isn't the slope the negative of A divided by B from just a few minutes ago? So the slope of both of them, -3/2, they're parallel. Okay, let me move on to the perpendicular. I'm going to use one of the same lines. I want to come up with an equation of a line that's perpendicular to this one. Tell me how I should write it down.
TY.
Now both of these signs are positive, right? 3x plus 2y. Don't I need to change one of them? So do I need to change them as far as reposition the 3 and the 2 and then change one of their signs? That work? So how about 2x and 3y, and let's make this one negative. Is that going to work?
No.
Just make up a number to plug in there. What's the slope of the first line? We just did that. -3/2. What's the slope of the second one?
2/3.
It'd actually be the negative of 2 over -3, right? Which is 2/3. Is that what we want to happen? Okay, perpendicular? So if you're handed that, you can pick off the slopes, or if you're handed one of them, you can kind of generate your own slope just by switching the two coefficients of x and y and negating one of them. That'll develop an equation that is linear. All right, from page A16, I'd like for you to look at these problems, make sure you know how to do these. This should review us on circles and lines, slopes and perpendicular and all this. Some of these are quick and easy. Just look at it and jot down an answer. Others require a little bit more effort. And that'll finish us in day 4, and we will continue tomorrow. Thank you.